Hey everybody, Corey and Victoria here. We are the Professors Du Bois, and in this video we're going to apply the ideal and combined gas laws that we talked about in a previous video lecture. We're going to apply them to some problems so you can see how they act in action.
All right, we're going to be talking about ideal gases. And an ideal gas is one that when the molecules collide, they have no loss in energy. Kind of picture like billiard balls hitting each other and bouncing off of each other, and if there's no loss in energy, we call that a perfectly elastic collision, and that's what ideal gases have. And they also occupy no volume. Now this obviously is not true. There's nothing that occupies no volume, but we kind of make this assumption that, okay, well, if it did occupy no volume and the collisions were perfectly elastic, then we would have really easy calculations, and we like easy. So if we treat them as ideal gases, our calculations get much easier, and we end up with being able to calculate and getting very close. So they're not perfectly ideal, but we can get very close by making these assumptions. And most gases do behave ideally at room temperatures and at atmospheric pressure. So this is where we're doing our work anyway, and most do behave ideally. So it's okay to use this assumption.
So here's our ideal gas law, and we're going to use this if we have just one sample of gas with one set of conditions. So when you look at your problem, if you had like two different pressures, we're not going to use this. But if you had a pressure and a temperature and an amount, and you were asked to solve for the volume, we can use this equation. Notice R. R is a constant, and the constant has the value of 0.082057 with units of liters times atmospheres over mole times Kelvin. So we have to be very conscious of our units so that they all cancel. So our T is temperature, N is the amount, has to be in moles, that temperature has to be in Kelvin, forgot to say that. The volume has to be in liters, and the pressure in atmospheres.
Anytime you use R, you have to be in those units. So here's an example. So if we have a 22.2 liter tank and we have a certain amount in moles, we don't know what the gas is, and we have a pressure. What's neat about this ideal gas law is it doesn't matter what gas it is, all will behave this way, and it really just depends on the amount in moles. So if we put in our values here, and we can solve for pressure, we set it up, we can divide by 22.2 liters on both sides. We're going to just try to walk through this very carefully so you can see how we did the math. Notice how all of the units cancel. And if you calculate this out, you get 5.6553 in your calculator, but you have to go back to the problem and take a look and see what your significant figures were, and we need 2 for this, so 5.7 atmospheres. So we're going to kind of derive the combined gas law from the ideal gas law. So if we start with PV equals nRT and we divide both sides by NT, we get PV over NT equals R. Well, we talked about R. R is a constant, so R is always R. R equals R. And if we say R equals R, that means that PV over NT also equals PV over NT. So this is where the differing sets of conditions comes in. So if you change conditions, then the gases will still follow this PV over NT equals R.
So this is what you're going to want to use when you do have, you're reading your problem, you have two volumes or two pressures. I like to kind of pull the data out to the side, and it just helps me see if I have two. So two sets of conditions, we're going to use this equation. And the cool thing about this is if something's the same on both sides, we can just eliminate it. So we can make this equation smaller or not. I mean, if it said you had, a constant temperature and they gave you the temperature, we could put it in both sides. That would be fine. And another thing I really like about this is because we don't have R in the equation, we can use different units. So if our pressure was in millimeters mercury, that's okay. We don't have to convert it. So here, if we had a constant temperature and a constant amount, we could just eliminate those and say P1V1 equals P2V2. Now, does that sound familiar?
That's Boyle's. Can you go back to, I want to just point out, so this PV over T is something that you'll see oftentimes as the combined gas law. But the N is also there, but when you use this, it's because you have the same sample of gas. And this is very common, to have the same sample of gas and then we changed its conditions. So here, if we're eliminating pressure because it's constant and we have the same sample of gas, then here we go. You end up with Charles' law. So the combined gas law on top here, this PV over NT equals PV over NT, is really a combination of Boyle's, Charles, and Avogadro's laws.
So here's another example. I've got a volume in milliliters and a temperature in Celsius. I've got a pressure in atmospheres. And it said, what would be the pressure? So I have a pressure, and they want to know what a different pressure is going to be. So that's two sets of conditions. So the can was left in a hot car, and it warmed up. So I've got two temperatures. I've got one pressure. We want a second pressure. Now, what about the volume? Did that change? It did not. So we can just take the volume out, or I could leave it in. It wouldn't affect because it's the same on both sides of the equation. So I can really simplify this though just by going P1 over T1 equal to P2 over T2. The temperatures have to be in Kelvin.
Always,
I know.
always.
And you know, you can get a little loose with when you don't have R. We can leave the pressure and in millimeters mercury, different units, but the temperature does have to be in Kelvin. So we did have to do a conversion there. Always convert to Kelvin. We get our new pressure, 5.01 atmospheres. Now, would you expect that? Does this make sense? At a cooler temperature, there was gas pressure, these moving molecules hitting the side of the container, force over area. And if it was hotter, they'd be moving faster. Hotter temperature is more increased average kinetic energy, so we would expect the pressure to go up.
Nice. All right, so here's another one. And we are going to have to decide what we're going to use to solve this. So we have a pressure gauge on a 2.5 liter tank, okay?
There's a volume.
We have a volume. It's of nitrogen, okay? So we know what gas it is, and we have a pressure. It says if the temperature in the room is, now we have a temperature, always with gases, we're going to have to put that in Kelvin.
Yeah.
So C means, okay, we got to put that in Kelvin. How many grams of nitrogen are in the tank? So here we put it into Kelvin. It's one single sample at one set of conditions. So this means we're going to use PV equals nRT. We're not changing conditions. We're just going to solve and find out the moles, and then we can go to grams.
That's where this one gets a little tricky because there isn't grams in the equation, but we have pressure, volume, amount in moles, and we can go from moles to grams. As long as we know what the gas is, it's nitrogen, and be careful, that's N2. So when you get the molar mass, we're going to have to use the molar mass of nitrogen. But I'm getting way ahead of myself. First thing we have to do is put our units into PV equals nRT. And you can see here we've got PV on the left equals nRT, and then we're just moving everything to the left, getting N by itself. When we solve for N, we get this number in our calculator. We can go to 3 sig figs based on our data from the question. We've got the number of moles, and now we're going to use the molar mass, that's N2, nitrogen gas, to get the number of grams. See how moles cancel? So we put the 28.013 grams on top over 1 mole.
All right, here's your practice. So you have 4 questions here. Please pause the video and give this a shot. Don't forget that temperature is always in Kelvin. All right, here's your answers. So we tried to give you a little bit of guidance in red, how we approach these, the first couple, and the third one you can kind of apply the same rationale to those to decide what to use.
Yeah, I think one thing worth mentioning here is question 2 was a little bit funny. I mean, we took nitrogen gas and added it to a flask containing oxygen gas, and this is okay. We're going to be doing a lot more of this in the future. It's moles of gas. Remember how much 1 mole of gas occupies at 0 degrees C and 1 atmosphere, right? 22.4 liters. Doesn't matter what the gas is.
Right. So the key here is it doesn't matter what gas it is. Doesn't matter if you mix it together. Moles over, in this case, pressure over moles equals pressure over moles because we have a constant volume and a constant temperature. So go back to that the combined gas law and just cancel whatever is constant. And in this case, we had temperature and volume. So we have a pressure and moles relationship. Doesn't matter of how you, what gases are in there. It's kind of neat. It's very strange. There we go. There's us. We look awful happy.
End of the semester. We're getting to the end of the semester.
Thanks for coming back to A Place to Learn Chemistry Where You Matter, the Professor's Du Bois channel. Bye-bye.